Hello everyone, welcome to my video on existence theorems. So this notion is extremely important because knowing that a solution exists is valuable information for mathematicians. So it's kind of like if you're looking for your favorite shirt, it's lost somewhere in your room and you spend hours looking for it and you just can't find it. You start believing that maybe a sibling took it, maybe you lent it to a friend, it was never returned, maybe the shirt's just not there. So spending time looking for something that may not be there is not what we want. Knowing that the shirt is there, let's say your mom comes in and says, no, I saw your shirt in your room, you just have to find it. Well, you're going to work or look twice as hard for that shirt, and knowing that it's there is comforting. You don't have that voice in the back of your head that says that maybe it's not there and you're spending your time looking for something that just isn't there and wasting your time. Another analogy we can make is like in chess. If I give you a chess position and you start analyzing, you spend hours on end looking at this position and you're trying to look for the winning sequence, well, a part of you might believe that it's not there. And you might be thinking, let me just make some move. But if we take that position, put it into a chess engine, and it tells you, no, you have checkmate in 2, well, knowing that checkmate in 2 is there, you're going to look twice as hard knowing that there's an actual win. So knowing that a solution exists is extremely important. And this is why we like our existence theorems. So we already actually saw one. The first existence theorem that we saw was the extreme value theorem, EVT, where it said that if you have a continuous function f defined on a closed interval, it attains the max and the min. So we knew that the max and the min were there, we just didn't know how to find it. So looking for the solution is a different question, but knowing that the solution is there is what we like, and that's extremely important to us. Okay, so we're going to look at a new one now called the intermediate value theorem, or IVT. So IVT states that suppose f of x is a continuous function. So again, we have a continuous function defined on a closed interval. So continuity defined on a closed interval, and let L be a number which lies between f of a and f of b, such that f of a does not equal f of b. Then there exists a number c in this interval from a to b, such that f of c equals L. Okay, so what is this telling us? Let's go ahead and draw a sketch of the function. This is the y-axis, this is the x-axis. Let's say we have our starting point here. We have our closed interval at a. This is a. You have b over here. Notice that it says that f of a does not equal f of b. So the y values for a and b cannot be the same heights. So we have f of a here, f of b up here. So they're not equal, they're not leveled out. And you have some continuous function that connects a to b. So I'm just going to draw a straight line. Let's say we have a straight line. What IVT is telling us is that there's a number L, there's a number C in between A and B, such that it hits the function at L, and L is in between f of A and f of B. Okay, so this is essentially what IVT is telling us. I'm not going to look at the proof, I'm just giving you the idea. And how do we apply this? Why is this useful for us? So typically what we do is we consider a positive and negative. In application, we look at a positive and a negative value. This is x, this is y. And let's say this is a. We're starting down here. And this is b. We're finishing up here. This is f of a. This is f of b. And we have some function. It doesn't necessarily have to be a straight line. It could be any type of function. So let's say we have something like this. As long as it's a function which is continuous. So I was able to sketch it without lifting my pencil. Well, essentially what we have is a value here which is negative, and a value here which is positive, right? This value here on the y is negative. It's on, let's say this is the origin. This is our x-axis, this is the origin. Well, we know this y value here is a negative value, and we know this one here is positive. So if you're able to find a value, some a where the function is negative and another b where the function is positive, well, what IVT is telling us, at some point, in order to get from this value here to this value here on a continuous function, it's impossible to get there without crossing the x-axis, without having a root at 0. And in this case here, it's not just one root, we could have more than one, so it's at least one root. And notice that we have to hit the zeros, and in this example, or this little drawing that I drew, we actually have 3 roots. We have 3 places on the graph where it crosses the x-axis. And this is what IVT is telling us. Okay, so it's impossible to get from here to here. Notice that f of a and f of b have to be different values. They can't be on the same level. They can't both be, let's say, over here on a straight line. One has to be different than the other. And if you could find one that's negative and another one that's positive, well, then that means in order to get there, you have to cross the x-axis. Okay, this is IVT in a nutshell. So I just want to add that over here we have 3 different c values. Let's call this c1, c2, and c3. And at c1, c2, c3, notice that c1, c2, and c3 are all in the interval from a to b. They're all within this interval, a to b. And at the same time, f of c1 equals f of c2, which is equal to f of c3, which is all equal to 0. Okay, so this is what this is telling us. There exists at least a number c in our interval AB such that f of c equals L. In this case here, if you're using the fact that it's negative to positive, your limit is in fact 0. So we have f of c equals 0. So in this first example over here, it says to use IVT to prove that the equation over here has at least one solution or root between 0 and 1. So the equation that we're dealing with is x to the 5 plus 5x equals 5. Okay, so in order to use IVT, what we have to do is first ensure that the function we're dealing with is continuous. Is this continuous? First, let's express it as a function. In order to do so, you set the equation here equal to 0. Why 0? The reason being is that we're going to look for a positive value and a negative value, and if we obtain a positive value and a negative value, then we know the continuous function at some point has to cross the 0. Okay, so let's set this function, this equation here equal to 0, and call it a function. So I'm going to move the 5 over, and we're going to consider the function x to the 5 plus 5x minus 5. Okay. So I brought the minus 5. Okay. So we're saying the equation equal to 0, minus 5 equals 0, and we're going to consider its function. Okay. What we want to do now from IVT is show that in this interval between 0 and 1, we get a positive and a negative value. Okay. Before we do that, we have to ensure that this function here that we're considering, is it continuous? Well, yeah, it's continuous. It's a polynomial function, and we know that polynomial functions are continuous. Okay. So we have continuity. So we have continuity, that's good. Now we have to find a negative value and a positive value. So what we have to do is essentially test points. This is the issue with IVT. We don't know which points, we're just kind of guessing. So we're going to try to plug in the endpoints 0 and 1. Let's see what happens when we plug in 0. So if we plug in 0 into the function, f of 0, we get 0 to the 5 plus 5 times 0 minus 5. This gives us negative 5. So when we plugged in 0, we got a negative answer. Okay, so all we really care about is the sign. This is negative. And let's see what happens when we plug in 1. We're hoping to get a positive answer. If so, we're done. So 1 to the 5 plus 5 times 1 minus 5. This gives us 1 to the 5 is 1 plus 5 times 1 is 5 minus 5 gives us 1, which is positive. So when we plugged in 0 and 1, we got a negative and a positive. That means that in between 0 and 1, there has to be a root by IVT. Since this gave us a negative, this gave us a positive value, at some point the function has to cross the, let's maybe draw a little sketch over here, just to convince you. We plugged in 0, we plugged in 1. We don't know what this function looks like. But we do know that when we had 0, it was down at negative 5. So let's say negative 5 is down here. It's not drawn to scale. So we have this point here. And when we plugged in 1, it gave us positive 1. So let's say like over here. Not drawn to scale. We have to connect this with a continuous function. So I don't know how to do this, or I don't know what this function looks like, but I know at some point, or at least at one point, it's going to have to cross the x-axis. There's going to be a c value here where it crosses the x-axis, where f of c is equal to 0. Okay. So there exists at least one root. There could be multiple, but we know there exists at least one, and that's what we wanted to know. That's what IVT gives us. So to conclude our statement here, what we showed is that we have to state that we're using IVT. So by intermediate value theorem, so by IVT, there's a symbol that we use for there exists. So there exists. This is a quantifier. So the notation that's used for a quantifier is a backwards E. So backwards E just means there exists. So if you ever see me writing there exists with a backwards E, this is what it means, okay? So there exists a value X or a value C. This value C in between the two intervals that we had from 0 to 1. So there exists a C in between 0 and 1. Those are the two values that we tested, the interval that was given, such that, or sometimes I abbreviate it ST, so if I do that, ST just means such that, and the last step is f of C equals 0. So we showed that there exists at least one root by IVT. So this concluding statement here is always the same. The only thing that changes is this interval where you tested your values. The second you get a positive and a negative value, that's the interval you're using here. So essentially the rest always stays the same. Okay, so this has to be memorized. Okay. Let's take a look at another example. So in this example over here, it says to use IVT to prove the equation has at least one solution or root, and the equation that's given is cos of x equals x. So let's go ahead and do this. Another thing I want to mention is here I'm telling you to use IVT. What if it doesn't say use IVT? How do we know it's an IVT problem? Well, the key word here is at least one solution. Whenever it asks to find at least one, that's IVT, because IVT gives us at least one solution. We don't know, again, what the solution is. We just know there exists at least one answer. So let's go ahead and solve it. So we begin by considering the function cos of x equals x. So consider f of x. Again, we set this equal to 0. So think of it as cos of x minus x equals 0. You could bring over the x or you could bring over the cos. It doesn't matter which way you do it. It's really up to you. So I'm going to bring over the x and it becomes negative x equals 0. And now I'm going to consider this function. So f of x equals cos of x minus x. So we're considering this function over here. What do we need in order to apply IVT? We need continuity. Do we have continuity here? Is this function here continuous? So the answer is yes. Why? You have to explain why this is continuous. So what's the cos function look like? We know the graph of a cos function. It looks something like this. It goes at 1 and it oscillates between -1 and 1 forever. Okay, so this continues forever. Okay, so we know cos of x is continuous based off its function. That we know x is just a polynomial, so we know well, it's essentially just a straight line. So we know a straight line is continuous. And the statement we have to use here is the difference between two continuous functions is again continuous. Okay, so that's what we're using here. So whenever you're adding, multiplying, or subtracting continuous functions, it's still continuous. Okay, dividing continuous functions as well, as long as the denominator is not 0, and the composition of continuous functions are continuous as well. So here the difference of continuous functions is continuous. So let's write that difference of continuous functions is again continuous. This is important because again, if you don't have continuity, your whole argument, like, it doesn't hold. Okay, the whole argument fails. You need continuity, so you have to state the function that you're dealing with is in fact continuous. Good. Now that this is done, we have to plug in values that are going to make the function one positive, one negative. And here, there's no interval that's given. So we have to kind of just attempt guess values over here. So we have to try values in here that's going to make this thing positive and try values in here that's going to make this thing negative. So let's go ahead and do that. So f of, what values are we going to take? Let's take values that we know. So maybe an easy value for cos is 0. We know from our unit circle what cos of 0 is. So we have cos of 0 minus 0. Cos of 0 we know is 1, minus 0 is 1. So we got a positive answer. So when we plugged in 0, we got a positive answer. Now the next value that we need, it has to be negative. So what's the next value that we should try? I don't know, it's really up to you. Since you have a quotes, you're probably going to want to choose values that are on the unit circle. So maybe pi over 2 pi, 2 pi or something. Let's go ahead and try pi. If we substitute pi, we have cos of pi minus pi. Cos of pi, from our unit circle, we know it's 0. Sorry, not 0. We know that cos of pi is -1. Sorry about that. Yeah, so if we sketch our graph, cos starts up here. So at 0, it's 1. At pi over 2, it's 0. And then at pi, it's at -1. Okay, so sorry about that. So cos of pi is -1, not 0. And then minus pi. So -1, you subtract pi, this value is negative. So there you go. We got a value that's positive, we got a value that's negative, so we could apply IBT. So now we use our statement. So we state that we're using IBT. So by IBT, there exists, so we said we're going to use the backward Z, there exists a value C in the interval that we chose. So we chose 0 and pi, such that as t, f of this value C is equal to 0. And we're done. So we showed there exists at least one solution. So in this example of here, number 3, it says to use IBT to prove the equation has at least one solution or root. And the equation we have is ln of x equals 5 minus 2x. So pause the video, try this on your own, see if you can get the right answer. Okay, so let's go ahead and do it. And notice the other thing is you might have an interval that's different than mine, and that's okay. As long as you get a positive value and a negative value, that's good enough. So obviously the smaller the interval, the better it is, because it's more concise and you're getting closer to the real answer. But at the end of the day, IBT, all we care about is having at least one solution that exists, and then later on we'll worry how to find the actual answer. So here we have a logarithmic function, so let's go ahead and ensure that it's continuous. First we have to consider the function. So we set this equal to 0. So we consider the function ln of x, bring the 5 over, it becomes minus 5, bring the -2x over, it becomes positive 2x. So is this function here continuous? Are we dealing with a continuous function? Yes. This is continuous because logarithm functions are continuous on its domain. So it's continuous for all positive x values. So it's continuous for x greater than 0. Okay, so we're using strictly positive values, because if you have negative values and you say it's continuous for all real numbers, that's wrong. Okay, so we have to ensure that we're only taking positive values. Okay, because logarithms only are continuous on their domain, and their domain is all x values that are greater than 0. Log of 0, if you plug into your calculator, you're gonna get an error message, or log of a negative answer, if you plug into your calculator, it's gonna give an error message as well. So make sure you're dealing with positive. You have to state that you're working with strictly positive values. Okay, and over here, minus 5 plus 2x is a polynomial, so adding or subtracting polynomials are polynomial functions are continuous, and adding or subtracting by a continuous function remains continuous. Okay, so it's continuous for all your positive x values. Okay, so that's the first statement that we need. So now we have to plug in values, replace x values, you can't use negatives, and get a positive and a negative answer here. So I don't know which values you tried, but if you tried f of 0, which is always a good one, using 0 is a good one to use. In this case here, it wouldn't work because log of 0 doesn't exist. Again, strictly positive values. So the first one I'm probably thinking of is 1. Let's substitute 1 into this function. Substituting 1, we get ln of 1 minus 5 plus 2 times 1. ln of 1 is 0, minus 5 plus 2 times 1 is 2. This is 5 plus negative 5 plus 2, giving us negative 3. So plugging in 1 gave us a negative answer. Okay. Let's try another value. Again, we have to take a positive value. So let's try, I don't know, 2. We have ln of 2 minus 5 plus 2 times 2. Ln of 2 is about 0.69. Let me use a calculator. Yeah, 0.693 minus 5 plus 2 times 2 is 4. This gives us negative 0.3068. So it gave us a negative value. So could we state by IVT that we're done? That we have a solution in between 1 and 2? Well, the answer is no. They didn't change sign. They're both negative. You have to ensure that you change sign, because if you have a negative and a positive, then that tells us that at some point the continuous function had to cross the x-axis. So in this case, this is not good. You have two negative answers. You have to ensure that the signs switch. So let's go larger. This seems to be getting closer to positive values. So let's try 3. F of 3 equals ln of 3 minus 5 plus 2 times 3. Okay. So ln of 3 is a positive value. Minus 5 plus 2 times 3 is 6. So 6 exceeds negative 5. So our answer here is positive, plus this value is positive. So this is going to give us a positive value. Let's go ahead and plug it into our calculator. Plus 6. This gives us about 2.098. Okay. But at the end of the day, we just care about the sign. So the fact that it's positive, that's what we wanted. And now we're done. So we found the negative value and we found the positive value. And you can choose which interval you want. So you could say in between 1 and 3, as long as you choose one that's positive and negative. Okay, so I'm going to take 2 and 3 because they're closer. So we conclude by IVT, there exists a C. There exists a value C. In the interval, I'm taking 2 to 3. Again, you could have taken 1 and 3, such that we have a root, f of c equals 0. Okay, so there's a solution somewhere in between 2 and 3. We don't know what it is, and to find it is very difficult, but we know at least there's going to be a solution between 2 and 3. Okay. So I hope this helped. This is an intermediate value theorem and the application. Next, we're going to move on to a new existence theorem.